Let's continue with what we were doing in the previous lecture. I am trying to prove this theorem that if x is an affine variety, that the function field of x is just the quotient field of the affine coordinate ring of x, which is the same as the ring of regular functions on x, and if y is a projective variety, then the function field of y is actually the degree 0 part of the homogeneous localization at 0, okay. And of course Sy localized at 0 itself will have a, being a homogeneous localization, will have a gradation, and it is the degree 0 part of that. If you take the degree 0 part, you get a field, okay. Right now I will explain more about this soon. So but so this is the point. The point is that we define something in geometric, okay, and then we try to capture it using commutative algebra. I mean that is the translation from algebraic geometry commutative algebra, and what this is what the theorem tells you what this translation means for the function field, okay. If it is an affine variety, then the function field is the quotient field of the affine coordinate ring. If it is a projective variety, then it is given by this, which also produces a field, okay. So let us try to prove that, and then I can use this to go and show also that there are no non-constant regular functions on a projective variety, okay. So here is a proof. So we start with x, an affine variety, x is irreducible closed in some an, and well, ax is, you have ax is just by definition this affine coordinate ring of x is just the ring of polynomials in n variables, namely the polynomial functions on this affine space restricted to x, okay. So this is by definition a of an divided by the ideal of x, which is just and a of an is just can be identified as polynomials in n variables over k, the ring of polynomials in n variables over k. These variables xi's are the coordinate functions on the affine space, the n coordinate functions, and here is your ax, and by the way, since x is affine, this is the same as ox, these two are one and the same, okay. And what I am trying to show is I am trying to show that kx is the same as the quotient field of ax, alright. So yeah, so So you know we already have that Ox sits inside Kx. This is something that we have already seen, okay. In fact any regular function is also a rational function. After all, Kx is supposed to be represented by regular functions on open sets, and Ox is regular functions defined on all of x, and all of x is also an open subset of x, okay. Therefore Ox is a subring of Kx, okay. This is something that we have already seen. I've mentioned it here. Ox sits inside any local ring, and that further sits inside Kx, which is the function field of x. And on the other hand, Ox is the same as Ax, okay, and Ax has its quotient field Q of Ax, okay. Any integral domain sits inside its quotient field, which is the quotient field is the same as field of fractions. Any integral domain sits inside its quotient field, okay, and there is a property which says that you know the quotient field is the smallest field in which the quotient field of an integral domain is the smallest field in which the integral domain sits, okay. That is also called the universal property of the quotient field or field of fractions, and therefore since Qax is the quotient field of Ax, which is the same as Ox, it is the smallest field which contains Ox, and since Kx is the field which contains Ox, okay, this has to be contained in that. Therefore you know you get a unique ring homomorphism from here into this, okay. So this ring homomorphism is a unique ring homomorphism which just expresses the fact that an integral domain sits inside its field of fractions or quotient field, and the quotient field is the smallest field which contains that integral domain. So if some other field contains that integral domain, then this quotient, there is an isomorphic copy of this quotient field inside that field, okay, and that is what is given by the image of this map, which is an injective map. And in fact it's pretty easy to write out what this map is. See, what is the quotient field of Ax? You see Ax is given by polynomials f and g. Ax is just Ox. Ox is regular functions, but here the regular functions are just restrictions of polynomials, okay. So you take an element of Ax, it's a polynomial modulo this ideal, okay. So you can write it as f bar, okay. So if I take a polynomial in n variables, namely f, then there is this quotient which is going modulo the ideal of x, and f goes to f bar, which is an element here, okay. And of course f bar is the coset f plus Ix, okay. So you have this f bar. So this quotient field will consist of things like this. There will be things of the form f bar by g bar, okay. So because of the field of fractions of an integral domain consists of all fractions, okay, quotients of two elements of the integral domain with the denominator element not being 0, okay. So the g bar cannot be 0. So this is how an element here will look like, okay. And what is the element to which you will send it? After all, f bar by g bar, if you think of it as after all as a function, this is just f by g, okay. After all, f bar, what is f bar in Ax? What does it mean? It is simply restriction of the polynomial f, which defines a function on this affine space, to the subset x. So geometrically f bar is actually f restricted to x, okay. F bar is what you get algebraically. It is a coset. It is read of, it is reading f modulo Ix, but geometrically what is it? It is simply restricting the polynomial f to this closed subset x, the subset x. So you know, so if you take f bar by g bar, you are just actually restricting f bar, you are just evaluating f by g, and where does f by g make sense? Where g does not vanish, okay. And where g does not vanish is an open set. It is an open set in the affine space, so if it intersects x, you will get an open subset of x, okay. So the moral of the story is that this will define this x intersection dg comma f by g. So this is, I have this element which makes sense here. So what you must understand is that you see dg is the basic open set in affine space where the polynomial g does not vanish, okay. dg is just the complement of z of g, which is the 0 set of g, okay. The 0 set of g is the 0 set of points where g vanishes, okay, and mind you that's a that's a hypersurface, okay. Of course g need not be irreducible, but even if you factor g into its irreducible factors, then this zg will be a union of those z of those gi's, which where the gi's are the irreducible factors of g, and each zgi will be a hypersurface, okay, which means a codimension 1 subvariety, okay, that is n-1 dimensional closed subvariety of an, okay. So this zg will be a union of hypersurfaces and its complement is dg, which is a basic open set. Mind you, this is a basic open set in the affine space and this is itself isomorphic to an affine variety, okay. By the Rabinowitch trick, this is isomorphic to a closed subset of an plus 1, okay. So this dg is an open subset and x intersection dg is an open subset of x, and there f by g makes sense, right. And so this is how you define this map, okay. And that's how this map is defined. This is how you will define this map naturally. You can check that this here I have defined this map in a very geometric way by thinking of everything as functions, but then I told you this map also comes because of the universal property of the field of fractions of an integral domain, okay. You can check that there also the definition is the same, okay. So this map that you get either geometrically or via commutative algebra, it's one and the same map, alright. And so all this tells you that the quotient field of Ax is certainly a subfield of Kx, okay. What I am to prove is that they are equal, okay. So what I will have to show is that I have to show this map is surjective, alright. And how do I show that this is surjective? Well, take so let me call this map as something, well okay, let me call this alpha, okay. So alpha is an injective K algebra homomorphism, K algebra homomorphism. Well, actually it's more, actually the quotient field of Ax contains K, quotient field of Ax is a field, it contains K, the scalars, they are all thought of as constant functions. Mind you, K is sitting inside here, K is every element of K defines a regular function, namely constant functions, so it is the same K here. So the constant functions are there, and this is a field which contains this smaller field, so this is the field extension and this is again another field extension, okay. Kx is a bigger field extension. In fact, we want to show that these two fields are the same, okay. Why is alpha surjective? Because how does an element in Kx look like? And any element of Kx is of the form well, is of the form u comma f, u comma phi, where well phi is in OU and u inside X is open, non-empty, right. I mean this is how we define Kx. Its equivalence classes of pairs consisting of an open set and a regular function on that open set, okay, and this open set has to be taken to be an open set inside X, right. And but then you see a little bit of thought will tell you that this is the image of an element from the quotient field of Ax, and what is that element is very easy to guess by just concentrating attention at a single point. So if x belongs, small x is a point of u inside x, okay, then phi looks like f by g, right, with x belonging to dg. I mean, this is how a regular function is defined. A regular function is something that locally surrounding each point looks like a quotient of polynomials. So phi looks like f by g means the function phi from u to k can be identified with the function f by g, which is also defined on an open neighbourhood of the point x to k, and of course that open neighbourhood should be a neighbourhood where g does not vanish, so it has to be in dg, okay. Of course x is in dg intersection x, which is an open neighbourhood of small x in capital X, right. This is just the definition of regular function, okay. But then you have f bar by g bar. This element, if you take f bar by g bar, that is certainly an element in the quotient field of Ax, certainly, and alpha of f bar by g bar will be, you will get this, as I have defined this map alpha, it is just going to be x, it is going to be x intersection dg comma f by g. This is what I am going to get, okay. But then notice that this is the same as and of course, you know, but this is the same as w f by g, these two are the same, where w is the open neighbourhood of small x in x intersection dg, where phi is equal to f by g. See, after all, phi looks like f by g locally at every point, so I am taking only one point, it is enough to take just one point, to call that point as small x. So there, for this point small x, I have an open neighbourhood w, okay, which is in x intersection dg, okay, and there on that w phi is the same as f by g, okay. That means, you know, so f by g makes sense on w, phi also makes sense on w, and so this is the same as w comma phi, okay, and that is the same as your u comma phi, because that is the equals. This is w comma phi restricted to w, so I should write phi restricted to w. I mean, the restrictions are obvious, let me not write it, okay. So in other words, so this implies alpha is this, alpha is surjective, and you are done. Thus the quotient field of x is the same as, well, this isomorphism is alpha as I have defined it, it is a quotient field of the function field of x kx is the same as the quotient field of Ax, okay, which is the same as quotient field of Ox, because Ox is the same as Ax, okay. So it is very simple to get the function field of a affine variety, simply take its coordinate ring and take the quotient field, that is it, okay. That proves the first part, okay. Now we are going to prove the second part, which is about the projective case, right. So how do you prove that? So let you start with y be irreducibly closed in Pn, Pm, okay. Y is a projective variety, and I am trying to now calculate the function field of y, alright, and then of course the projective space is a quotient of the punctured affine space above and the homogeneous coordinate ring of the whole projective space is the same as the affine coordinate ring of the affine space above, and this is just polynomials in m+1 variables. Okay, and the homogeneous coordinate ring of y is just this modulo ideal of y, where ideal of y is all those homogeneous polynomials which vanish on y. So this is IH, I will put a subscript h to just remind you that it's a homogeneous ideal, it's a ideal generated by homogeneous elements, namely it is generated by all those homogeneous polynomials in these m+1 variables which vanish throughout the locus y. Okay. Now we have seen in earlier lectures that that the projective space has an affine cover consisting of m+1 open subsets which are each isomorphic to affine M space. Okay, so we have Pm K is union of ui I equal to 0 to m. Ui is just the complement of the 0 set of xi. Okay, this is a 0 set in this is a projective 0 set, this is a 0 set in Pm. Each xi is a homogeneous polynomial of degree 1, its 0 set will define a closed subset of projective space. It's called the hyperplane projective hyper, it's called the projective hyperplane defined by xi, vanishing of the xi, and its complement is this ui. Okay, and these ui's are all open sets, and we have seen that there are isomorphisms phi from ui to am. Okay, there are isomorphisms like this, and you know how these isomorphisms are written. Ui corresponds to all those points with projective homogeneous coordinates with ith coordinate not 0. So what you do is, if you take a coordinate like this, which is written as lambda naught through lambda m with colons to indicate that it is a common, that it can be scaled by a common ratio, these are the homogeneous coordinates, you simply send it to lambda naught by lambda I, lambda m by lambda I, where you omit lambda I by lambda I. This is the map. This is a map that is defined set theoretically, and we proved that this map is an isomorphism of varieties, and under the isomorphism of varieties this translates to, this is a geometric map and it translates to commutative algebra to an isomorphism of the affine coordinate rings, namely A of amk. So this is by pullback, this is pullback of regular functions, and give me a regular function here, you compose with this, you get a regular function here, that is a map like this, the opposite direction, and this is a K algebra isomorphism. This is of course isomorphism varieties. Okay, and here I will get O of ui, and we proved that what this O of ui is actually it is the coordinate ring of Pm localized at xi, and then you take degree 0 part. Okay, so we proved this. So we have proved this in an earlier lecture, right? And now this is the picture with the whole projective space. Now you rewrite the picture that corresponds to this closed subset y. Okay, so what you will get is, if you intersect with y, you will get y also as a union of I equal to 0 to m y intersection ui, okay. So y is covered by these y intersection ui, and each y intersection ui is an irreducible closed subset of ui, and under the isomorphism phi it will give you an irreducible closed subset of affine space, so it will correspond to an affine variety. So this just expresses the projective variety as a union of at most m plus 1 affine varieties. So we used this to show that any projective variety is a union of affine varieties, and we later on proved that any quasi affine variety is also a union of affine varieties, and therefore we proved that any variety is a finite union of affine varieties. So the affine varieties are the building blocks of all varieties. Anyway, so you have this, and what happens is that what happens to this isomorphism, this y intersection ui you will have an isomorphism phi, the phi will give you an isomorphism with phi of y intersection ui, which is a variety there, and what will happen is that and if you will translate, if you go to commutative algebra, this will translate to A of the affine coordinate ring of phi of y intersection ui, which is an affine subvariety. Phi of y intersection ui is a irreducible closed subvariety of am, okay, and again this is phi star, which is pullback of regular functions by phi. Okay, this is also a K algebra isomorphism, and what you are going to get here is the ring of regular functions on y intersection ui, and we proved that this can in fact be identified with S of y. You localize at xi and then take the degree 0 part, okay. So so it's this thing, when you intersect with y you get this, alright, and now here is a point. The point is, well, ky is the same as k of y intersection ui if y intersection ui is not 0, is not empty, okay, because I told you that the function field is not going to change if you go to a non-empty open subset. Y intersection ui is a non-empty open subset of y. I mean, of course I am choosing an I such that y intersection ui is non-empty open subset of y. If some y intersection uj is empty, I do not choose that j, okay. That is certainly at least one I such that y intersects ui, okay, and you take that y intersection ui, that is an open subset of y, non-empty open subset of y, it has the same function field, but then k of y intersection ui is the same as k of phi of y intersection ui. This is equal to this because y intersection ui and phi of y intersection ui are isomorphic, because phi is an isomorphism. But then so this is the function field of phi of y intersection ui. Phi of y intersection ui is phi of y intersection ui is a subvariety of am, okay, and so it's affine, it's an affine variety, and we have just now proved here in the first part that if you have an affine variety, then the function field is given by taking the quotient field of the quotient field of the ring of regular functions, namely the affine coordinate ring. So this is the same as quotient field of the affine coordinate ring of phi of y intersection ui, okay, and of course here when I put equality, maybe I should put here isomorphism, because I am using the fact that if two varieties are isomorphic, then their function fields are isomorphic. So I have this isomorphism between y intersection ui and phi of y intersection ui. These two are isomorphic varieties. Isomorphic varieties have isomorphic function fields, okay. So that is a fact that is pretty easy to understand, I didn't state it, but let me try to write that down here. Suppose you have x, so let me use some other notation. Yeah, so if x1 is a variety and x2 is a variety and phi is an isomorphism of varieties, then I have phi star, the pullback of functions will induce an isomorphism of kx2 with kx1. Okay, so if two varieties are isomorphic, then their function fields are of course isomorphic. The idea is very simple, because you see, if you give me an element of kx2, it's going to be a rational, it's a rational function, so it's a regular function, an open subset of x2, and if you pull it back, you will get a regular function on the inverse image of that open subset in x1, and that's going to define an element of kx1, and you can check that this is an isomorphism. It's a trivial check that if two varieties are isomorphic, then their function fields are isomorphic. Okay, so an isomorphism of varieties induces an isomorphism of function fields in the opposite direction. Always the isomorphism at the level of regular functions, or at the level of local rings, or at the level of function fields. Okay, all isomorphisms that involve functions either locally or globally, they are all induced by pullback. That's something that you should not forget. Okay, so isomorphic varieties have isomorphic function fields, and since y intersection ui is isomorphic to phi of y intersection ui, they have isomorphic function fields, but the quotient field of phi of y intersection ui is the quotient field of its affine coordinate ring. Okay, that's what we have seen in the first part, and then, but this is the same as well, you know, so this is the same as quotient field of, this is isomorphic to the quotient field of O of y intersection ui, because again if two rings are isomorphic, if two integral domains are isomorphic, then their quotient fields are isomorphic. So the quotient field of this is isomorphic to the quotient field of this, because these two integral domains are isomorphic. But I have already identified O of y intersection ui with sy localized at, so this is just the quotient field of sy localized at xi, take this degree 0 part, and now I want you to check, it's a very simple check in commutative algebra, that this is the same as simply sy localized at 0 and take the degree 0 part. Okay, so it's the last equality that has to be checked, and it's kind of it's very easy to check. Okay, because you know, so this is the only thing that needs to be checked. This is the only thing that needs to be checked. So you must understand what I am doing here. Here I am using the fact that if two varieties are isomorphic, their function fields are isomorphic, and here I am using the fact that if two rings are isomorphic, two integral domains are isomorphic, then their quotient fields are isomorphic, and then I come to this. Okay, and yeah, so how does one prove this last equality? That's also a little bit of commutative algebra. So let me rub this part so that I can continue. So well, so what is sy localized at xi is just it is just elements of the form f by xi to the power of r, equivalence classes like this, where f is a polynomial in these m plus 1 variables, and r is greater than or equal to 0. I mean, this is what it is, and the square bracket is equivalence classes. Okay, this is what the localization is. Sy localized at xy is just invert xy. Okay, invert xi means you are allowing denominators with positive integral powers of xi, right? And what is sy xi localized at 0 is, well, it is such things which with a homogeneous degree 0, which means that the numerator should also be homogeneous, denominator should also be homogeneous, and they should be homogeneous of the same degree, so that when you take the difference of degrees it is 0. Okay, so this will consist of things of the form sums of finite sums and of course also finite products for that matter. Well, I could simply write it instead of saying all that, I could simply write it as f by xi to the power of r, such that f is homogeneous of degree r. This is the degree 0 part, right, and of course the degree 0 part sits inside this. Okay, and what about this? So that is and if I take the quotient field of this, okay, this is an integral domain, all right, and I take its quotient field. So if I take quotient field of s y xi at 0, this is what this will sit inside, and this will consist of quotients of things like this. So it will be something like f by xi power r divided by some g by xi power s. It will be quotients like this, where f g homogeneous of degree r and s respectively. This is what it will be, all right, if I take the quotient field of that, right, and well and what you can understand is that I can identify an element like this with the element f times xi power s by g times xi power r. Okay, this, if you just divide these two very naively, this is what you will get. Okay, and the numerator will have degree r plus s, denominator will have degree r plus s. So this is the quotient of homogeneous polynomials of the same degree. Okay, so what you are going to get is you are going to get an element here. Okay, so see, this belongs to sy localized at 0, degree 0 part. I will tell you what this means. See, sy localized at 0 is equal to is gotten by inverting all non-zero homogeneous polynomials. Okay, this is, the notation is ring localized at a prime ideal. Okay, so the point what I want you to notice is that this is homogeneous localization. See, normally when you localize a ring at a prime ideal, you are supposed to invert everything outside that prime ideal. Okay, but here it is homogeneous localization. What you are doing is you are not inverting every non-zero polynomial, but you are inverting only non-zero homogeneous polynomials. The reason why you are inverting only homogeneous polynomials is because only then this localization will get a gradation. Okay, if I mind you, this sits inside sy localized at 0. So this, when I write like this is the usual localization. 0 is a prime ideal, and ring localized at a prime ideal is invert everything outside that prime ideal. So this is actually the quotient field of sy. This is quotient field of sy. This is very big. This is very big because this consists of quotients where in the denominator you have put any polynomial which is not 0. In fact, you are inverting even non-zero homogeneous polynomials. even not, I mean sorry, you are in fact you are inverting even non-homogeneous polynomials, alright, but this is smaller, you are inverting only homogeneous non-zero polynomials, only those homogeneous polynomials which are non-zero you are inverting them. So this gives you a subring of this which is the quotient field, okay, but this is graded because the gradation can be defined as degree of the numerator minus degree of the denominator, because the denominator consists only a homogeneous polynomial which is non-zero, because you are here you are inverting only the non-zero homogeneous polynomials, and in this if you take the degree 0 part, that is what this is. So this consists of exactly elements like this, okay, this consists of exactly elements which are given by numerator homogeneous polynomial, denominator also homogeneous polynomial, they are both of the same degree, okay, and therefore you can see that this is certainly sitting inside this homogeneous localization degree 0 part to which this belongs, and that is a map. You send this guy to this guy, alright, and you can check that this map is injective, alright. What we are trying to say is that this is also surjective, that is what we want to prove. We want to show that this there is an isomorphism between this and this, okay. I have written equality, but in most cases the equality is just isomorphism, with proper identification an isomorphism can be treated as an equality. I mean if you think of this function as the same as this, okay, as a function, then you get equality, but if you prefer to write it like this with all these weird brackets here and another weird bracket here if you want, okay, then you can think of it as a formal isomorphism, okay, but if you just think of them as functions, it is just equality, right. So so this is sitting inside this, and conversely you know you can check that if you give me any element here, it comes from an element here, okay. So so the only fact that needs to be proved is that this is surjective, alright, and how does one show that? It is very simple. Conversely, you know, see, if you want, let me call this map as alpha sub I, let me call this map as alpha sub I. So I just want to say that alpha sub I is well an injective K algebra homomorphism. Of course, you know, see, the fact is that this is a non-zero homomorphism from a field, and you know a non-zero homomorphism from a field is always injective, so you do not have to worry about verifying the injectivity because its source is a field, alright, being the quotient field of this integral domain, alright. I have to only worry about the surjectivity. So how do you get surjectivity? Surjectivity is also pretty easy. Well, take an element here. How does an element here look like? It will look like a quotient of two homogeneous polynomials of the same degree, alright. So take f by g, take a quotient in this, which means that f and g are homogeneous of the same degree, and of course g is not 0 because whatever you put in the denominator, whatever you invert is non zero. So any element here looks like this, and I want to tell you that this element actually comes from an element here, okay, and that is perhaps pretty easy. You can easily see that I just have to divide by the same power of xi as the degree of f, which is the same as degree of g. So it's obvious. So you can see that. So it's surjective, obviously. So clearly this element f by xi degree of f divided by g by xi degree g, this element, this fellow is in Sy localized at xi degree 0 and its image under alpha I is f by g. Okay, so that implies that alpha I is an isomorphism, is surjective, hence an isomorphism. Okay, as functions, if you consider everything as functions, then these two are not just isomorphic, they can even treat them as equal. Okay, so this proves the other fact that ky is nothing but, take the homogeneous coordinate ring of y, you localize at you take homogeneous localization at 0 and then take the degree 0 part. This is an isomorphism. Okay, so that proves the theorem. Okay, so so it's very clear that you know how to write commutative algebraically what the function field is for an affine variety or for a projective variety. It helps you with calculations. Okay, and there's another fact that comes with in connection with these two diagrams. The fact is the following. The fact is that, of course, the function field is an extension of the base field small k. Okay, and the fact is that the transcendence degree of the function field O of a variety over small k will give you the dimension of the variety. Okay, so that's also true. So you know, so here is a, so that's a very very corollary. Corollary is if x is affine, dimension of x, this topological dimension of x is the dimension cruel of Ax. This is also the dimension cruel of Ax at mx where x of the local ring. This is also equal to transcendence degree over small k of the quotient field of Ax, which is the same as transcendence degree over small k of the function field of x. And mind you that this guy is the same as this is isomorphic to O x small x, and this guy is isomorphic to Ox. So this is one corollary. So you know you have so many formulas for the dimension of an affine variety. It's either the topological dimension of x, or it is the Krull dimension of Ax with the ring of polynomials restricted to x. Okay, or it is also the Krull dimension of the ring Ox, which is a K algebra. Okay, it's also the Krull dimension of Ax localized at mx, because you know Ax localized at mx is the local ring of capital X at small x. Okay, and this is the same as the transcendence degree of the quotient field of this, and that is the same as the transcendence degree over k of over small k of capital Kx. So this is one important corollary, and if you have and you know the point is that if it is projective also all these statements are correct, except that you don't bring in the global regular functions, because as I told you, we are going to prove that for a projective variety all the global regular functions are all the only global regular functions are all constants, okay. So if y is projective, then you know I'll have to forget this, okay. This is the only thing that I have to throw out, but everything else can be written. So let me write that out. If y is projective, then also you will see that dimension y, topological dimension of y, is the same as the Krull dimension of the local ring of y at a point small y, and there is also the transcendence degree over small k of the function field of y. This is what will happen, okay. And so why is this a corollary of all that we have seen? I have to explain that, and the see, we have already proved the topological dimension is the same as Krull dimension of the affine coordinate ring for an affine variety, and but you know but then you know if you take the Krull dimension of the local ring, okay, then you see the Krull dimension of the local ring is just the Krull dimension of this, okay, but the Krull dimension of this is actually the same as the height of this maximal ideal, okay. See, because when you localize at a prime ideal in the local ring, the only prime ideals that survive are the prime ideals which are contained in the localized prime ideal, in the prime ideal that you are localizing, okay. So what is one thing in commutative algebra that you should remember about localization? If you take a ring, if you take a commutative ring A, and if P is a prime ideal, if you go to AP, what are the prime ideals in AP? The prime ideals in AP are precisely the prime ideals in A which are contained in P. By going to AP, you are throwing out, you are removing all the prime ideals which are outside P, which have elements outside P. So by going to AP, you are actually only focusing attention on prime ideals which contain P. So you know the Krull dimension of this thing, this is a local ring, so the Krull dimension will be, it has only one maximal ideal, and you know Krull dimension of a ring is just supremum of the heights of all its prime ideals. So it will be the height, it will be here the biggest ideal is this maximal ideal, so the Krull dimension of this ring is the same as the Krull dimension of the height of this maximal ideal, but then this local ring modulo this maximal ideal is just the base field k, okay. This ax localized at mx modulo mx is just k, okay, and the dimension formula will tell you the dimension of k is 0, therefore the dimension of ax mod therefore the dimension of ax localized at mx is the same as the height of mx, okay, and but then that height will be equal to the Krull dimension of ax, okay, and that is the reason why you get this equality, okay. And this equality comes because any integral domain and its if you have a so this equality comes because of the fact that you know so this also comes from a formula that I have stated earlier. If you have a finitely generated K algebra which is an integral domain, then the transcendence degree of the quotient field of that integral domain is the same as the Krull dimension of that algebra, okay. So so if you apply that to Ax, you will get that this is equal to this, okay, because Ax is a finitely generated K algebra which is an integral domain, okay, and its transcendence degree over K has to be equal to the Krull dimension of Ax, okay. So that gives this equality, alright. So you do not get this is equal to this, rather you get this is equal to this, and therefore this is equal to this because these two are equal, okay. And of course we have proved Q of Ax is the same as Kx, so this is also equal to the transcendent degree over K of Kx, okay. And the same kind of argument will yield these equalities in the affine case, okay. And you have to only remember that when you if you want to do this for y, it is enough to do it for yi, where yi is an affine piece of y which is gotten by intersecting with ui, okay. And if you do it with instead of if to do this computation, it is enough to do this computation with y replaced by y intersection ui, which is yi if you want, okay, and then that case is already covered here, therefore this follows, okay, therefore that is the proof of this statement, okay. So I will stop with that.